Hello, my name is Masanobu Kunitomo. In this talk, I'd like to present our disk evolution models considering winds from the disk based on the papers published last year and in 2020. First, let me briefly introduce the current understandings of disk evolution. The disk lifetime has been constrained by observations, which is thought to be several million years. This figure shows the evolution of the disk fraction of each cluster. Red point shows the gas signature and the blue point shows the dust signature. And both gas and dust signatures disappear at around 6 million years. In the standard scenario, two processes are considered, namely accretion and photoevaporation. The disk is assumed to be turbulent, and the turbulent viscosity drives the angular momentum transport in the radial direction. The origin of the turbulence is thought to be MRI, and the viscosity is parameterized with alpha parameter. On the other hand, photoevaporation drives thermal disk winds. Photoevaporation is driven by the radiation of the high energy photons such as X-rays and UVs, and heated gas in the disk atmosphere exceeds the gravitational potential in the outer disk. So such gas can flow out from the disk. However, with this standard scenario, some observational features cannot be explained. So in this talk, I will focus on two questions. How does stellar evolution affect disk evolution? How do disks with weak turbulence disperse? And first, let me start with the first question. As I introduced, photoevaporation is driven by stellar XUV irradiation. And the stellar XUV photons are emitted by three mechanisms. Stellar magnetic activities in the corona or chromosphere, accretion shock, and photosphere, if stellar surface is hot enough. The stellar magnetic activity is driven by convective motion in the stellar interior. So the stellar structure is important, or the thickness of the surface convective zone is important. For the photospheric radiation, the stellar effective temperature is important. And in this figure, I'd like to show the evolutionary tracks in the HR diagram from 0.5 to 5 solar mass stars. The horizontal axis is effective temperature, and the vertical line is vertical axis is luminosity. And the dashed line here shows a verse line where pre-main sequence phase starts. So here, the stellar age is 0. And the dashed dotted lines show the 1 million year and the 10 million year isochrons. These isochrons indicate that 4 solar mass and 5 solar mass stars evolve rapidly. They reach main sequence within 1 million years. On the other hand, for example, 1 solar mass stars reach their main sequence at 40 million years. So higher mass stars evolve more rapidly. And here I like to emphasize two key features. First, the effective temperature of high mass stars increases with time before the disk dispersal rapidly. The other key feature is the stellar structure evolution. The low mass stars are on their highest track, so they have free convective structure. On the other hand, high mass stars lose their surface convective zone quickly and becomes radiative. So the XUV luminosity of young high mass stars are expected to evolve rapidly. And these are important for the XUV luminosity. So we simulated the disk evolution, including the effects of stellar evolution. We solved the 1D diffusion equation, considering viscous accretion and time-dependent photoevaporation. We combined the photoevolution model in the literature and XUV luminosity evolution using the stellar evolution models, atmospheric models, and empirical relations. And simulation settings are shown here. So let's move on to the results. This figure shows the disk evolution around 3 solar mass stars in the radius surface density diagram. In this plot, the evolution looks similar to the standard picture. First, accretion dominates and surface density decreases with time. And once accretion rate decreases down to the photoevolution rate, a gap opens. In this case, a gap opens at about 1 million years. And both inner disk and outer disk quickly disperse. However, in this slide, I'd like to stress the importance of the stellar evolution. This figure shows the evolution of the photoevolution rates. Blue, magenta, green lines show the X-ray, FUV, EUV photoevolution rates, respectively. And in the previous studies, photoevolution rates are assumed to be constant with time. But if we consider stellar evolution, these evolve with time significantly. And also, interestingly, the dominant mechanism changes from X-rays to FUV. The decrease of the X-ray photoevolution is driven by the structure evolution from convective to radiative. The magnetic activity becomes less efficient and X-ray luminosity decreases with time. The rapid increase of the FUV photoevolution is induced by the increase of the stellar effective temperature. The photosphere becomes hot enough to emit FUV, and FUV luminosity increases rapidly here. So we conclude that stellar evolution is crucially important for the realistic disk evolution models around the intermediate mass stars. We performed disk evolution simulations from 0.5 to 5 solar mass stars. And this figure shows disk lifetime with stellar mass. We found that the disk lifetime decreases with stellar mass, which has been suggested by observations. So our results are consistent with observations. The evolution of FUV luminosity plays an important role in the disk evolution in the intermediate mass stars, shown by the magenta region. And disks around low mass stars are mainly dispersed, mainly due to the X-ray photoevolution. Okay, next I'd like to talk about evolution of disks with weak turbulence. Recently, both observations and observational and theoretical studies have suggested that disks are not so turbulent. The alpha value is suggested to be less than 10 to the minus 3. For example, ALMA observations have shown that disks are geometrically thin and the velocity dispersion is not so large. On the other hand, theoretical studies have shown that non-ideal MHD effects suppress MRI. So disks would be MRI inactive and alpha is expected to be low. But if we consider only the viscous accretion and the photoevolution, previous studies have suggested that the disk lifetime exceeds 10 million years. So this is inconsistent with observations. This figure shows the disk lifetime with viscosity alpha parameter. And with alpha less than 10 to the minus 3, the disk lifetime exceeds 10 million years. So we need additional input physics, and we examine the MHD effects which are not considered in the classical picture, namely magnetic winds and magnetic accretion. We investigate disk evolution considering viscous accretion, which is less efficient, and magnetic accretion and magnetic disk winds, and also of the operation. Theoretical studies and MHD simulations have suggested that the magnetic force can drive disk winds in addition to photoevaporation. And the magnetic braking drive the accretion. But here we focus only on the disk evolution around one solar mass star, and stellar evolution is not considered. First, I'd like to show the disk evolution without photoevaporation. In this figure, we can see that the disk structure is significantly affected by the magnetic winds and magnetic accretion, in particular in the inner region. However, the disk lasts long. In this model, even at 20 million years, disk remains, so inconsistent with observations. This is because MHD winds are driven by accretion energy. So wind mass loss rate decreases along with decreasing accretion rate with time. So the MHD winds are self-regulated, and we cannot reproduce the observed disk lifetime only with MHD disk winds and accretion. Next, let me show the model with MHD effects and photoevaporation. In this case, the inner disk lifetime is about 3 million years. So this is consistent with observations. This is because, unlike MHD winds, the photoevaporation rate does not decrease in the late phase, and therefore drives quick dispersal. Finally, this figure shows the mass loss profile of the MHD disk winds and photoevaporation rates shown by the green lines and blue lines, respectively. We can see that MHD disk winds dominates in the early phase in the inner region. On the other hand, photoevaporation is dominant in the late phase in the outer region. So we conclude that these winds are cooperative, and both winds should be considered in the realistic disk evolutionary models. So this is a summary of this talk. Stellar evolution should be considered in the disk evolution models around intermediate mass stars. And photoevaporation and the MHD winds are cooperative, and both winds should be considered. Thank you very much for your attention.